Okay, we continue. This is number 17. This is page 3 of the Fun Times with Antidifferentiation packet. So this is where we left off from last time. I think these are good problems. What should we do? Well, here it's very obvious that some chain rule happened here because, well, I see a composite function, e to the inner function being 4x cubed, and the derivative of 4x cubed is 12x squared, which is, give or take, a constant, exactly what we have here. So yeah, it does look like some chain rule happened here. So we can recover this by doing the u substitution. So we let u be 4x cubed, and then du dx is 12x squared, so du is 12x squared dx. And I am missing only a 12, so I stick in the 12, I undo the damage with a 1/12, and this becomes 1/12. 12x squared dx is du, so this is just e to the u du. And the antiderivative of e to the u is just e to the u, so this becomes 1/12 e to the u plus c. So this is 1/12 e to the 4x cubed plus c. Okay, that was pretty easy. 18. Okay, what do we do now? This is e to the 1 over x over x squared. Okay, this is maybe also not so hard, I don't know. Perhaps it's helpful if you rewrite this in antidifferentiation friendly form. So e to the 1 over x is really like, well, it's like e to the x to the negative 1. And this x squared, maybe some will find this helpful, is really just x to the negative 2. Okay, and if you write it like that, I think it's more obvious that the derivative of x to the negative 1 just is x to the negative 2, give or take a constant. So once again, this is of the form e to the something where the inner function is x to the negative 1. So if you let u be x to the negative 1, then du is negative x to the negative 2. Well, negative x to the negative 2, du dx is that. And so du is negative x to the negative 2 dx. Okay, and that's basically what I have there, except I'm missing just a negative. So I put in a negative on the outside and a negative on the inside to cancel it out, and that leaves me with, by just a direct variable substitution, negative. Instead of e to the x to the negative 1, I write e to the u, and instead of negative x to the negative 2 dx, I write du. And so, once again, it's pretty straightforward. Okay, antiderivative of e to the u is just e to the u, so this is negative e to the u plus c, and our final answer is therefore negative e to the 1 over x plus c. Cha. And yeah, that's it. Okay, 19 is even more straightforward. Oh, I suddenly gave more space and only put 6 problems per page for some reason now. I think I can squeeze this in here. Number 19 is antiderivative 3x minus 2 to the 4th. This is about as straightforward as it gets. Inner function 3x minus 2, outer function to the 4th. I let u be 3x minus 2. Du dx is therefore 3. Du is therefore 3 dx. So I want there to be a 3 there. There isn't one, so I stick it in and undo the damage with a 1/3. And then this whole thing therefore becomes 1/3 u to the 4th du. And what is that? It's 1/3 times Well, the antiderivative of u to the fourth is u to the fifth divided by 5. So 1/5 u to the fifth plus c. So final answer is 1/15 times 3x minus 2 to the fifth plus c. Right, looking good, moving right along. Number 20. Let's see. Antiderivative x plus 1 over 3x minus 1 cubed, then dx. Yeah, this is basically just a problem to push the idea, if you haven't realized already, that when it comes to antidifferentiation, if you can split things up into different pieces, do so. So here, I'm definitely going to split this up into the antiderivative of x dx, and the antiderivative of 3x minus 1 to the negative 3. And this is possible because this will give you the function, or a function whose derivative is x. This will give you a function whose derivative is 3x minus 1 to the negative 3. And it's because the derivative of the sum is the sum of the derivatives. So therefore, the antiderivative of the sum is the sum of the antiderivatives. Anyway, moving on. This we can just do by direct rule. That's just x squared over 2. This one you can almost do in your head, but don't, in my opinion. So it just takes almost just as much time to write out all this stuff, and I think for me at least my error rate basically goes down to 0 when I actually do the u-subs. If we were in class in person, I would really kind of get up in people's face. There's usually about 10 people per year who sort of rebel. It's usually like boys. And just refuse to do u-subs and just do the entire problem in your head. You will sometimes get the right answer, but you will often not get the right answer. So it's just really a bad idea. I swear to you that this method is good. So it's kind of just bookkeeping. So let u be 3x minus 1. Thus du dx is 3. And du is 3 dx. Okay. I need there to be a 3 in there. So I stick in the 3, undo the damage with a 1/3, and thus this whole thing becomes 1/3 u to the negative 3 du. And then doing this gives me, I go up a power to negative 2. Up a power to negative 2, and I hope I didn't make any well, whatever. Up a power to negative 2 and divide by negative 2, so that becomes 1/3 times negative 1/2, and u to the negative 2 plus c. So let's see, did I do that right? I did. And therefore, this whole problem becomes x squared over 2 minus 1/6 times 1 over u squared plus c, or really, x squared over 2 minus 1 over 6 times 3x minus 1 squared plus c. And that's looking great. Okay. What else? One more. I guess I can fit on this board. 21. Okay. This is the antiderivative of 5x squared over x cubed minus 2. Okay, this is hard. This is a new kind of thing, or at least I suppose it's new. And in our book treats this as an entire separate section, but I'm just kind of weaving it in here. Well, does it look like some chain rule happened here? Not extremely obviously so, but it is the fact that the derivative of x cubed minus 2 is 3x squared, which is, give or take, what we have here in the numerator. And so, if you're willing to kind of abstract, well, perhaps maybe what I could do is write this as, the 5 is sort of doing nothing, so it can just be taken out. And maybe what I'll do is I'll write this as 1 over x cubed minus 2 times x squared dx. And perhaps now you can see more clearly, and this is the pattern recognition that you just developed from experience and practice, that, that this is kind of the 1 over function. It's the 1 over function is the outer function, and the inner function is x cubed minus 2. And we know that the derivative of natural log is 1 over x. And since the derivative of natural log is 1 over x, the antiderivative of 1 over x is natural log. And so, what I'm now going to do is let u be x cubed minus 2, so that du dx is 3x squared, so that du is 3x squared dx. And then, noting that I'm missing a 3, I stick that 3 in and undo the damage with a 1/3 on the outside. So after all of this, what I end up with is 5/3 on the outside, and this 1 over x cubed minus 2 is 1 over u, and 3x squared dx is du. And now, perhaps you see, oh, this is just the antiderivative of 1 over u. And that is something that we know how to do. That's natural log. Okay, this comes up a lot, and so you have to sort of have done this enough times that you see this as a possibility, and kind of thinking one step ahead, anticipate this happening when you go to make this substitution. So anyway, finishing off this problem, this is going to be 5/3 natural log of the absolute value of u plus c. And the absolute value is there for technical reasons I don't feel like going into right now. See original video on antidifferentiation. Okay, so final answer, 5/3 ln the absolute value of x cubed minus 2 plus c. There's your answer. Woo! Good. One more problem from this page. Which is this one here. At number 22, the antiderivative of x squared over x minus 1. Okay, well, this is a rational function, and hopefully I have convinced you last semester that the best way to deal with rational functions and to really understand them is to do the polynomial long division. Here, the function is sort of begging to be divided. It's saying x squared divided by x minus 1. Well, let's just do the division. So anytime, and you should just do this every single time. Anytime you're given a rational function in which you can do polynomial long division, which is to say that the degree of the numerator is greater than or equal to the degree of the denominator, then you should. And when you divide x squared by x minus 1, you get, okay, that goes in x times, x squared minus x, you subtract, and you get x, that goes in 1 times, and you get x minus 1, so the remainder is 1. Probably did that right. What was the point of this? The point of this was that actually this entire rational function, x squared over x plus 1, is actually just x plus 1 over x minus 1. And now we see the benefit of doing this is that we've broken up this antidifferentiation problem into sort of 3 small antidifferentiation problems which I can do individually. The antiderivative of x is just x squared over 2 plus a constant. The antiderivative of 1 is just x plus a constant. And now we have this problem. Okay, almost everyone would just finish this problem off in one step by doing it in your head. And I guess eventually, you know, you should too. But for this moment, note that there's no specific rule per se for the antiderivative of 1 over x minus 1. And so we should let u be x minus 1, but then du dx is just 1, and so du just is dx, and so this can be rewritten as 1 over u du. And the antiderivative of 1 over u du, as we just mentioned, is ln absolute value of u, and so really this becomes ln absolute value x minus 1. Okay, so anticipating that, for those who are experienced, few people will actually go through all of this stuff I just did. Almost everyone will just jump straight here because it's clear that that the answer is just natural log of x minus 1. And that's because, well, because the derivative of x minus 1 is 1, the chain rule sort of doesn't change anything at all. But this is the long way, which I think beginners should do, but then maybe at some point you can start skipping some small steps. Okay, good. Woo! 2 pages down, 1 to go, but really 4 to go. Let's go to page 5. Oh, in which I only have 4 problems per page, but they're starting to get a lot harder. So antidifferentiation is hard. I guess maybe now is a good time to have this conversation for the people who are still watching, that this is not an algorithm. You will notice that there is sort of intrinsic to this process is some degree of creativity and initiative that you have to take. And you have to sort of notice patterns and look ahead and whatever else. So when it comes to differentiation, it's not like that at all. For differentiation, there's this finite list of rules. There's the product rule, the quotient rule, the chain rule, and you just sort of algorithmically follow them. In fact, I bet a smart person could program, you could do it maybe with given enough time, a computer to just differentiate any function, which is the sum, product, quotient, and composition of a certain set of known functions, because it's just completely recursive. But antidifferentiation is different. Mr. Stein, when he used to teach Analysis 1A 10 years ago, he used to give his students a project when it came time to doing antidifferentiation, and the project was they had to go buy a tube of toothpaste, and they had to go home and squeeze the entire tube of toothpaste out of the tube onto like a piece of wax paper or something, and that's differentiation. Easy, straightforward. Antidifferentiation is getting the toothpaste back in the tube, and that is really, really hard. And he assigned it as kind of a challenge, and they had to write do like a lab report all about it, and then to talk about their feelings. And the feelings are antidifferentiation, very, very hard. Differentiation, easy, in retrospect. Okay, whew. So yeah, maybe I'll just do like kind of one problem or something per, well, we'll see. Okay, 27, without further ado, we are on page 5 now. The antiderivative of 2 over 2x minus 1 quantity squared plus 4 dx. Alright, well, just immediately, even if I can't see far in advance, I am going to observe that this 2x minus 1 seems to be some sort of internal function. And so this seems to be a composite of 2 functions. So I'm going to perform a simplifying substitution, and just to simplify my life. So if I let u be 2x minus 1, then du dx is just 2. And so du is just 2 dx. Okay, great. Well, that means that given this side work, it means I can rewrite this problem as du over u squared plus 4. Okay, and that makes me very happy because that's significantly simpler than the problem that I just had. So I think that's worth it. Alright, so now the problem becomes, how do I antidifferentiate u squared plus 4? Okay, so here, some people might have an idea, and some people might have no idea how to do this. And if you can try lots of things, and trying and sort of failing is kind of part of the process of doing antidifferentiation. One thing you might try to do is a substitution. Like you could let w or something be, to pick a new variable that doesn't look like u, w could be u squared plus 4. But then when you try to go do like dw du, you get 2u, and that 2u is just not there. There's just no 2u. To put it another way, there is no back inside for the u squared plus 4. If u squared plus 4 were the internal function, then the derivative of it, when you apply the chain rule, would be 2u, but there is no 2u. Which is to say, it doesn't particularly look like someone did the chain rule here at first glance. So maybe we're all out of ideas. Oh wait, I have an idea. I happen to know that the derivative of arctan is 1 over x squared plus 1. Okay, this year we learned this just as school was closing, so maybe that means you didn't learn it. And even in a normal year, there are some category of students who just don't learn these formulas because they just hope that they will go away and never come back. Well, they're back. Why is the derivative of arctan 1 over x squared plus 1? The 1 minute version of this is that we set ourselves y equals arctan x, and we recognize that this relationship between x and y can be rewritten as tan y is x. That's just what the arctan of x is. It's the angle whose tan is x. And having done that, we may then differentiate both sides with respect to x. Sorry for this review, but maybe some people need it or want it. And what is the derivative with respect to x of tan y? It's secant squared y back inside for the derivative of y, because it's the derivative of tan of something. Derivative of tan of something is secant of something back inside u dx. Here we get 1. And thus I learn that dy dx is just cosine squared y. But what is cosine squared y? Well, then we sort of go back and make this picture, and there are sort of two cases to consider. The case where x is positive and the case where x is negative. I'll be lazy and just make one, or maybe I'll make sort of both pictures on the same. I don't know if this is a good idea or not, but so on the one hand, if x is positive, then this is x, and this is y, I meant to say, and I'm trying to make a picture of arctan. What is arctan? It's the angle whose tan is x, and so I need to make this x and this 1. And then this becomes root x squared plus 1. That's if x is positive, but if x is negative, I'll switch colors, although it might not be apparent from the video. But if instead x is negative, then the arctan of something negative will be a fourth quadrant negative angle, so I label that negative. And now, well, if x is negative, then this is what I get. And it's still true that the tan of this angle is x over 1, and it's still true that this is root x squared plus 1. So in both cases, I see that the cosine of y, cosine of the arctan, so to speak, is 1 over root x squared plus 1. Okay, this was just too slow. Cosine squared y is therefore 1 over x squared plus 1. And therefore, the derivative of arctan is 1 over x squared plus 1. Okay, I apologize if you didn't need that review, but this is how you, in 1 or 2 minutes, by yourself can recall all of the formulas for the derivatives of the inverse trig functions, and you actually need to know all of these formulas, kind of just by heart. Because if you don't know them by heart, you won't look for and recognize the patterns that emerge. And specifically, when I look at this du over u squared plus 4, it reminds me very, very much of arctan. You need to see that connection, so you need to have this formula like in your brain. And the connection is, man, I wish that 4 weren't a 4. I wish that 4 were a 1. If that 4 were a 1, I would be done. So how are we going to do this? We're going to do this by forcing that 4 to be a 1. And we can force that 4 to be a 1 by factoring a 4 out of the bottom. And so we get du over, well, if I factor a 4 out of the bottom, then that's not u squared anymore. That's u squared over 4 plus 1. But now, by a sort of crafty algebra move, I see that this can, the 4 I can just take out entirely, I guess. Then this is du over, but let me rewrite u squared over 4 as u over 2 quantity squared plus 1. And now I've sort of achieved what I wanted, which is to force this expression to be in the form of the derivative of arctan. Okay, so I will take it all out to the bitter end and let w be u over 2, so that dw du is 1/2, and that dw is 1/2 du. And that means that I want there to be a 1/2 here, so I stick in the 1/2 and I undo the damage with a 2 on the outside. Thus, after all this effort, I find that this can be rewritten as 1/2 antiderivative, 1/2 du is just dw, and this is just w squared plus 1. Okay, and I never antidifferentiate until I have taken myself all the way back down to the sort of bare formula. What is this? Well, it's arctan w plus c. And of course that really is arctan w is just u over 2, so it's really arctan u over 2 plus c. So really, it's arctan 2x minus 1 over 2 plus c. And that is the actual answer to this problem. Okay, and shortcuts are maybe available, but I think it actually is easier and better and more reliable to just kind of do it out the long way. Okay, 3 more problems. And page 6 of this packet is full of problems that were just like that one that I just did. Okay. 28, going in order. Okay, this is maybe sort of, this is maybe harder and easier at the same time. This is 1 over x root 4x squared minus 1. Okay, what now? Alright, well, extremely, diligent students will look at this and see, this looks like the derivative of arcsecant. And you are right. I am not going to redo this right now, because it takes like 10 or 15 minutes to do carefully, and there's a video I made for this. But remind yourself why the derivative of arcsecant is 1 over the absolute value of x times x squared minus 1. And since that's true, it's true that, okay. And then follow up to that, also don't want to really get into the details of this, but the derivative of the arcsecant of the absolute value of x is, if you follow the logic and split this up into cases, the case where x is negative and the case where x is positive, that the chain rule will sort of cancel itself out, and in fact what you get is 1 over x root x squared minus 1. This is actually not that complicated. You can think of the derivative of the arcsecant as telling you that the derivative is always positive, which is just true since arcsecant is always increasing. Looks kind of like that. Well, therefore, therefore if x is positive, it'll just be that, but if x is negative, then it will be the opposite of that negative number. What am I saying? If x is positive, then the root of x is, but if x is negative, then the derivative should be that for some reason. Well, I guess this just works out. I'm not giving a good explanation. But anyway, there it is. If you split it up into two cases, why is that true? Oh, okay. Because I guess one way to think of it is that the arcsecant of something positive sort of just deletes this left side of the graph entirely, and so the arcsecant of something will just look like that actually. So though arcsecant is always increasing, arcsecant absolute value x is decreasing and then increasing. So when x is negative, you do want it to be negative. All right. The point of all this, oh man, going too slow. The point of all this is that the antiderivative of 1 over x root x squared minus 1 is thus arcsecant absolute value of x plus c. Okay, if you don't totally understand this, it's not the most important thing in the world. And even if you forget the absolute value, it's also not the most important thing in the world. But there it is. I've taught it. Okay, well, does this look like arcsecant? Yeah, it really, really does. And I don't even think I have to do any fancy stuff here. I just can rewrite this 4x squared as 2x quantity squared minus 1. And because I'm always careful, I'm going to do the actual substitution of u equals 2x. So du dx is 2. So du is 2 dx. And so, since that's true, I need like a 2, right? So, but I need a 2 here, but I also need that to be a 2, because I want to do a variable substitution after all. So having done that, I then have this can be written as du over u root u squared minus 1, and then I apply the formula. But you have to know the formula, and the answer is it's arcsecant. Arcsecant absolute value u plus c. So the real answer is arcsecant absolute value 2x plus c. Okay, two more.